Section 13.7, Tangent planes and normal lines. In this section, we are going to look for equations of tangent planes and normal lines to surfaces, and in order to do that, we will be using del capital F. And we'll, of course, see how this compares to del F. And in the end, we'll just see how to find the angle of inclination of a plane in space. So, just a first note that looking for the normal line to a surface and looking for the tangent plane to a surface are basically the same problem, because in both cases what you need is a point and a vector, and it happens to be the same vector that you need. The vector for the line is the direction vector, it points in the direction of the line. For a surface, you need the normal vector, so it points perpendicularly to the plane. And that means the normal vector to the plane is the direction vector to the normal line. So what we saw in the previous section is that if we have a function of two variables, z equals f of xy, the gradient del f is a vector that is perpendicular to the level curve. And we can expand this to the next dimension. If we have a function of three variables, then del f would be a vector that is perpendicular to the level surface at a point in 3D. Therefore, there's a really clever trick that we can use here. We can take out the function of two dimensions, the function of two variables, here it's a surface, and we can create another function with it, which would be capital F equals f of x and y minus c. Alright, so I just did minus c here. And so that would be a function of three variables, but we will only look at one level surface. We will look at the level surface that is equal to 0, and which makes sense because this z equals f of xy can be rewritten as f of xy minus z equals 0. So among the four-dimensional function that we would have here, we only look at one of the surfaces, the one that is f of xy minus z equals 0. And that way, if we seek the perpendicular vector to this function, which is del f, we will get a vector that is perpendicular to f of xy. So, or to the surface given by f of xy. So let's look at an equation of a tangent plane first. If f is a differentiable function, then the tangent plane is going to be given by this very long equality here, and we are going to prove that. So we are looking for at a level surface f of xyz equals 0, and we are looking for the tangent plane at the point x0, y0, z0. To prove that, we're going to consider all the points xyz that are in the tangent plane. And notice that these points xyz in the tangent plane can make vectors that are in the tangent plane. X minus x0, y minus y0, z minus z0 is always going to be vectors that lie in the tangent plane because both points are in the tangent plane. Now what's interesting to notice is that because del f is perpendicular to the tangent plane, if we take the dot product of del f and our vector here, then it's going to be equal to 0. So if we set this up, del f dot product with v equals 0, which is a fact, and then we just expand, we get exactly the expression that was written above. So del f dot v is capital Fx times x minus x0 plus capital Fy minus times y minus y0 plus capital Fz times z minus z0, and it has to be equal to 0. So let's apply this to an example. find an equation of the tangent plane to the hyperboloid given by the expression, the implicit function here, or implicit relation here at the point 1, -1, 4. First, we build a function capital F of 3 variables, and we set that equal to 0. So we look at the level surface of this greater function, and that level surface corresponds to the surface we're actually interested in. And then it's pretty straightforward. We calculate each partial derivative, capital Fx, capital Fy, capital Fz. We plug in the point for each of them, and we can just plug in the values of the point and the gradient in the expression that we had. So capital Fx is equal to -4 times x minus 1, and so on. For the normal line, we saw that it's virtually the same concept. We are going to set up a function capital F of 3 variable such that the level surface we are interested in is equal to 0, and we take the 3 partial derivatives. This time what's different is that to find the equation of a line, we have to use parametric equations. So the line is x equals 2 plus 60, -2 minus 60, and -3 minus 40. This comes from the point and the directional vector. So again, the directional vector of the normal line is the same as the normal vector to the plane. The following exercise might look very complex, but in fact, there's a neat way to figure out the necessary information. We are given 2 surfaces here and here, so this one and that one, and there's a nice sketch here of 2 random surfaces in plane, and we are curious to find the tangent line to the curve of the intersection at a certain point. So first we have in black the curve of intersection of these 2 surfaces, but we are not looking for the equation of the black curve. We are only interested in finding the tangent line to that curve. All right, so we are looking for the equation of the red line. So because it's a line, we need a point and we need a direction vector. The point is given, it's 0, 1, 3, that's no problem. But how are we going to find the direction vector? And this is where the cross product comes in. We know how to find perpendicular vectors to each of these surfaces. They are shown in green. This green vector is perpendicular to this kind of vertical surface, and this green vector is perpendicular to the more horizontal surface. How are we going to find that? Using the gradient. Once we have these 2 green vectors, we can use the cross product with them, and that'll make a vector that is perpendicular to both green vectors, and therefore tangent to both surfaces. So that's really the clever step. And since it's tangent to both surfaces, it's going to actually be the direction vector of the line we are looking for. So the recipe that I explained is written here. And then the steps are written there. So we are finding the 2 perpendicular vector to the surfaces, just like we did in the previous exercise. So it's vector 0, 4, 12 and vector 0, 2, 1. And then we plug that in, and this yields the vector that is tangent to both surfaces. Therefore, the vector that is tangent, or is the direction vector of the line, and we can just plug the point and this directional vector in the parametric equations. Note that interestingly enough, but that's completely random, it happens that the directional vector of our line is -20, 0, 0. So it's a line that is actually parallel to the x-axis. But that's unusual, it's not typical, anything could have happened. Lastly, the angle of inclination of a plane. What that means is the angle that the plane makes with the xy plane. And we can do that using something we've done in the past. All we need to is a normal vector to the xy plane, and that's, you can pick any one, but the vector 0, 0, 1 is the easiest. It's the unit vector that we often call k. And so we just apply the formula that we've seen in a previous section, which is also the formula that we use when we look for an angle between two vectors. The only difference is that we put absolute values at the numerator, because the angle theta is never greater than 90 degrees. Think about it. How could you have two planes with an angle of more than 90 degrees? It would be leaning to the other side, and so we would measure the angle on the other side. That's not true of vectors. Vectors can go up to 180 degrees between them. So straightforward example, given the plane 2x minus 3y plus z equals 4, I find the normal vector immediately, 2, negative 3, 1, and I plug it in the formula. So there we go. Thank you for listening for this rather short section. Bye-bye.